Hello and welcome. Here we are in lecture 16. So we're shifting gears today. We've now spent 15 lectures prior today learning about Agile hardware design in theory, in practice. We're learning about Scala. We're learning about Chisel. We're going to do a few case studies of actually designing components. So what are we doing next? Well, to help prepare you for the project and beyond, we're now thinking more about what does your actual hardware component do? What is it actually designed to do? And so in particular, we're talking about how should you architect it for physical considerations. So that's something we've kind of largely ignored or hand waved prior to today. We said, oh yeah, this perhaps is less efficient, perhaps it's a longer critical path. So we're going to be a little bit more deliberate and talk about it a little bit more intentionally. Try to be careful about that. And so yeah, we're going to talk more about the physical concerns. And as a chisel level designer, you can take interventions architecturally that can really help improve those issues. And so the first place you can have an impact is actually how you use memory. So we'll talk about it today as well. Okay, so first I'm going to motivate why we're doing physical design optimization and motivate it. Talk about memories, then talk about how you can make interventions on behalf of memories. Okay, so why should we care about physical design? Why should we optimize it? Obviously for efficiency, right? We want to have an efficient piece of hardware. And efficiency is intentionally a very broad term here, right? That could be efficiency in terms of, absolute performance. It could be, performance per watt. It could be cost, whatever your metrics are. But the thing is, we can't always spend max effort on every problem, right? And so, to be agile, to be nimble, we want to keep thinking about when is this most important, when is going to give us the most bang for a buck, and when is this worthwhile. So we kind of want to be familiar with how much we can improve our design and what would it take to get those improvements, right? And so I'll spend maybe another minute kind of highlighting this. And a lot of times in software engineering, performance is something we kind of do half, second effort. It's kind of like, well, as long as I didn't get my big old complexity super wrong on this design or on this program, things are okay, right? And it turns out, perhaps a lot of software engineers spend a lot of time writing a lot of software without spending a lot of time thinking about optimizing it. For hardware, the optimization is actually pretty important, right? If you think about it, you're only going to build hardware if you have some efficiency goal. If you don't have an efficiency goal, you can almost certainly write software to do the same thing you want to do with your physical electronic, and that'll be a lot maybe cheaper or easier, right? 30, 40 years ago, capability of a microcontroller was, pretty poor. And so there's a lot of motivation for having, specialized logic for certain small electronics. Now in 2024, you can get, a 64-bit Linux capable core with its memory for under $1, right? So writing code is a great way to make a lot of things work. It was historically custom hardware. And so what that means is the thing that is still custom hardware in today's world, which is still plenty, are things where performance efficiency really matter. So if you're not thinking about that, you're not actually going to build a hardware, right? You build a hardware because you care about these things, right? That's kind of the key point. And so there's different levels, so you can kind of optimize and fix things in terms of the architecture, physical design, et cetera. And so we're going to try to approach that. And so as a good designer, like I said, see the big picture, understand how your thing goes, and kind of, okay, well, if I need to get some efficiency improvements, where are these for me to get it, and which levels of design? All right. In terms of what these metrics are, in software, usually it's just one thing, right? Performance. That's only one of three things in hardware, right? In hardware, we talk about PPA, or power, performance, and area. And they all have their own importance depending on the design, right? So for example, power. Of course, with mobile devices, we care a lot about our battery life. But of course, it goes both ways, right? You could have a more energy efficient thing as a result, increase your battery life, or if you improve energy efficiency for power, you could also shrink the battery size for the same battery life, make the device smaller. So you can kind of go either way. Obviously, things like heat for extracting power is important for thermals, and then even cost, right? It's not just how many joules you use and pay the power company for. It's also provisioning things. For example, in a data center, a lot of the cost is the physical structure to transmit and distribute all that power, right? So power is really has a lot of impact for cost, as well as these issues in terms of efficiency and stuff. And for high performance designs, power is often a limiting factor, right? We can build chips that go even faster, some absurd number of gigahertz, but we don't because that would be too hot, right? So power is really, really important. So perhaps why we often say figure is first. Performance also matters, right? We, want to a certain target. And then finally is area, right? Which in the case of a custom chip like an ASIC, right, that corresponds to cost. But even on FPGA, it also corresponds to cost as well, right? If you make your design smaller, you can perhaps get away shipping a smaller FPGA when you actually ship it as an electronics device, right? So there is definitely some things. So these are three metrics to go for. And because it's three metrics rather than one metric, it's hard to optimize all three at the same time, right? So oftentimes in a particular application, you think about one of them being, a limit, like I must meet this cost target or I must meet this performance target to be real time at this frame rate or something. And then perhaps you have one or two metrics you're optimizing for, or maybe one is fixed, it's like a target limit. Another one you're optimizing for, and the second one is a secondary optimization target. So there's some sort of hierarchy of optimizations in your particular design. Okay, so I think it's kind of highlighted, right? If you're going to go about optimizing, you can't just do this blindly, right? You need to think about what are you doing. So far in this course, you've often said things like, oh yeah, just write the hardware. But at some point, you think more about, well, what are you implementing the hardware with, right? Is it going to be an ASIC? Which process? Using an FPGA? Sometimes we'll make some tweak that's really good for one technology, won't be as good for another technology. Additionally, when it comes time to actually running tool flows, you have to provide constraints and metrics of tools, right? You can't just say, hey, CAD tools, here's my hardware design, make a chip for me. And it's like, no, I need more. I need you to tell me what technology. Okay, here's technology. Okay, I tell the technology, you tell it, okay, what's the target clock frequency? And it's like, well, you say, make it as fast as you can go. And it's like, that's not how it works. You just kind of give it a target and it works from there. So there's a lot more hand-holding involved, right? So as of course, in the Agile methodology, right, we want you to take this, see the big picture, right, zoom out, close the loop, and then start figuring out where you get your bang, right, where you get your benefits. And so make sure the things you're targeting are actually really problematic for PPA. Just like how in software, folks get really excited about fixing some function, which is a small fraction of the time and thus not worth optimizing. Same thing's true for hardware. You have this like thing you really were optimizing in hardware, and it turns out not in a critical path or it's not very much area. Don't worry about it, right? It's not impacting you. Make sure you go up to the right things. And despite all these challenges of hardware design, having a language like Chisel and a hardware generation methodology makes it actually easier for us, right? We have the ability to do things like have multiple alternatives already encoded. So we just flip a switch and we get option A versus option B. We can change some parameters to better perhaps size certain things to match the resources. And so if you think about it, right, in the long run, right, having a generator seems much likely to be portable across technology than having a single, fixed function instance, right? And of course, when you're doing all this, you're going to make trade-offs, right? Oftentimes you'll improve one metric at the cost of other metrics, time, space trade-offs, energy, cost trade-offs, that sort of stuff. Oof, I'll pause for questions. Yes. Oh, great question. So how much can you influence, I'm going to rephrase it. How much can you influence power from Chisel? Quite a bit. Depending on your implementation technology, this can vary, right? So for example, if you're using FPGA versus ASIC, there's some impact there. So for either technology, right, when you think about your power consumption, there's like your static power and dynamic power. We'll come to this later in the quarter, but I can kind of summarize it right now. So of course, static power, you can reduce that by shrinking your design, right? Dynamic power, you can reduce by changing how much bits toggle, right? And so, for example, things like, we had that queue optimization where originally we had our FIFO where we had this massive shift register, and we changed to like the MEM where we had things in place that with fewer bits flipping, that would be more power efficient. To your point about the clocks, yes. So, a now basically almost mandatory optimization, but 20 years ago was considered novel. Clock gating can now be done pretty reliably by some CAD tools if you get the right combinations of features and the right CAD tools. So what does that mean from the Chisel point of view? There's some small considerations about making sure which kind of registers you use in certain cases to make sure it's possible for the CAD tools to do the clock gating for you automatically. You don't want to be doing clock gating manually. You want it to be doing the clock gating for you. Additionally, if you really want to go after power, you can imagine clocking is not going to get done. You want to do power gating, right? You actually want to turn entire components of your design on or off or change sleep states. At that level, it's definitely an architectural visible feature, in which case that's going to appear inside the chisel. So maybe that kind of gets to your question, hopefully. Cool. Other questions? But yeah, so this is kind of the point, right? Is that we're trying to summarize all of hardware design in like, a few minutes. And so one of the fun things about this course is I love how we have three different communities coming together. We have the architecture people, the hardware design people, and the software people coming together, and all three of them have something to bring. So I try my best to like sometimes summarize some stuff from the other subfields, make sure everyone's on the same page. And so today is about getting everybody on the same page about hardware design and optimization for it. But by the end, we'll actually talking about architecture, which are things like I wish I could talk about in an architecture course, but I do not because they're too low level, but we can talk about it in this course, and that'll be fun. Um, cool. Other questions? Yes. The floating point unit in the TPU? So okay. So I don't, I'm not sure I fully understand the question. So please correct me if I get it wrong. So within AI hardware accelerators in a broader picture, a common way to optimize is to, use fewer bits, right? If you can use fewer bits, that's less hardware. And if you use fewer bits, it's a great question for explaining today's topic. So I'm happy you asked this. So yeah, if you use fewer bits, that's less hardware, right? If you use fewer bits, that's less hardware, less cost, also less power. Or alternatively, for the same amount of hardware, you can get more numbers, perhaps giving you more performance. And so, for the last 10 plus years, when you're building optimized hardware for AI, there's a lot of time spent thinking about just how many bits of precision you need for your numbers and the format. So you can have fixed point or floating point. And even amongst floating point, historically it was always, this IEEE 754 standard, the common thing you always used. But nowadays for AI, they found that those the choices made for IEEE standard weren't quite what AI wants, and so they would prefer a different ratio of exponent to mantissa, different dynamic range, and so that sort of stuff. And so yeah, there's all sorts of other uh, numeric formats arising. So in the case of the TPU, if I might get this wrong, so maybe put a caveat on this. I believe you said it was bfloat, which uh, there is both bfloat, which is a standard I believe Google is pushing that people are using. There's also a block float. And so, so they're not optimizing the term bfloat too much. And so the bfloat, my understanding is it's like they changed the bit allocation between a mantissa and exponent and floating point representation. So that's, once again, a design level change that's going to show up in your chisel, right? And you can imagine how, gee, if I had a generator, boy, would that be an easy change, right? Oh, I want to change the amount of bits in my exponent and my mantissa. That's like, two character change. Boom, done. Go chisel, do it, right? That's perfect. Alternatively, the block floating point is an opportunity to recognize you have multiple numbers going at the same time, so they actually can share the exponent across multiple floating point numbers at the same time. So I can't promise that a TPU fully memorized. I believe, the older ones definitely had certain precisions, and newer ones have more precisions. They have some flexibility, but yeah, I would not be surprised if it supports that bfloat format. Is that your question? I guess, yeah. Okay, yeah. Oh, great question. So comparing the logic simplification from what I write as chisel to get spit out as Verilog, and then given a CAD tool, Verilog to the actual hardware, how does that logic synthesis optimization look? So chisel has some logic optimization built in. It does pretty cursory stuff that is hopefully almost guaranteed to be beneficial. If you study logic optimization, you will find that your target implementation topology really matters. And so, for example, maybe you want to reduce gate count. If you're on FPGA, for example, maybe you have like only 5 input LUTs. Actually, you want to have more inputs per gate, right? So it really depends on technology. But in spite of that, there is some very cursory stuff inside of Chisel. It is not going to be as sophisticated as a full-fledged CAD tool, and it can't be, right? Because a full-fledged CAD tool, when it's running, it knows what technology you're targeting. So it's going to inherently have more information. That being said, a few points to note. One, I'm very familiar with the internals of the Scala-based backend flow using Fertile. So to as the SFC, the old version. The new MFC, which is part of Chisel 5, Chisel 6, uses a different set of code. I believe that technology in there, because it's somewhat derived from LLVM, maybe keep a little more sophisticated optimizations. If not now, hopefully in the future. One point. The other point is that there are some chisel designs out there where the person realized there's an opportunity to optimize, and leaving it to the end for the physical design CAD tools, they might miss some opportunities. And so as a result, things like Rocket Chip internally actually had an implementation of Quine-McCluskey, a classic optimization algorithm, to run on the decoder, to actually optimize the decoder for you. So that was actually a Scala level logic optimizer within a single design. That's pretty heavy lifting, right? Normally your chisel design shouldn't be that complicated. But example, what's been done. Cool, great questions. Yeah, sure. Either, right? Yeah. So you're saying who chooses the implementation technology? So that's usually, a choice way above your pay grade, so to speak, right? Um, like I said, there's usually some small choices you can make. Okay, which foundry you're working with. You're doing an ASIC, right? Okay, well, which foundry you're working with is a big thing. It's not just a small one-off choice. It's a big decision, right? And even with a given foundry, which technology you're using is also a big decision. Even for a given technology node, there might be subtle variations. Okay, this is like, this one versus the higher low voltage process, higher low VT or multi VT, whatever. There are some knobs there. Um, it's one of those things where you'll often will perhaps literally try multiple ones and see how the numbers look, or you'll try to use your best guesses going into it. Um, I would say hypothetically, where you use as a chisel designer have the most impact. Perhaps actually if your deployment's going to have the FPGA base, because in that case you could, change FPGAs isn't as drastic as changing process technologies. And so if you were to go for a certain FPGA and decide later on you need a bigger or smaller one, that's not so crazy. Is that okay? Cool. Great. No, I appreciate the questions today. This is a good day for questions. Okay. So we've already kind of dove off the cliff a second ago about hardware design concerns, but imagine you're coming from software world and you've been spared the unfortunate experience of running hardware CAD tools. I wanted to alert you to how it's not quite the same. So in software, which I'm jokingly calling easy, which of course isn't easy, but for today, it's hard people who can say it's easy. When you're coding up something, right, most of your effort goes into coding something. You also spend some time on verifying it. Obviously, sometimes even half your time on verifying. But you're mostly working on the code and writing the code. And how do you evaluate it? Well, beyond correctness, of course, you care about performance or something, right? And when you optimize it, if you have a better algorithm, that's more efficient, that's probably more efficient on most CPUs. Not always, but most modern CPUs are big superscalar out of order cores, and so it's pretty transferable, right? And the best part is when you use the compilers, they're pretty good, right? You basically give a compiler, here's the plus file, go. And it's happy with that information. You don't need to tell it too much more. You can give it more flags, but if you give it just that amount of information, it'll still give you a very serviceable binary, right? And the other thing is that regular compilers pretty rarely have errors. Like, I've been programming for over 20 years. I've encountered what's determined to be a compiler, error, like actually causing it to produce incorrect assembly, only like 4 or 5 times in my career. I've had compilers crash on code of compiling because it's too big or complicated more often than that. But compilers, if they give you assembly and actually give you a design, it's almost certainly correct, right? And guess what? The compilers that gave me incorrect assembly, I'm going to name names. ICC, I don't want to use it anymore, right? Twice is enough. Once I was already really doubting it, but twice I'm like, it's dead to me, right? Because there's so much effort getting software correct. Who would want to actually spend time debugging a broken compiler? Like, no. So in that community, there's basically zero tolerance for buggy tools. Unfortunately, it's not the case for hardware. And so the hard world of hardware design, what do we have, right? Simply just getting the design, in other words, your RTL, in this case it's Chisel, but it could be Verilog, whatever. Even just getting that functionally complete and correct That's only, some of the effort. Which in software, that was like most of it. Getting your code implementing correct, that was most of the effort. In hardware, it's only a fraction of the effort, right? You still have to like actually make physical design, whether it be making a chip design or mapping FPGAs and really verifying it. Those are huge efforts, and you really want to make sure it's really, really right, especially if you're making a chip, because you don't want to do a respin, right? You don't want to have to do multiple runs. Additionally, when it comes to optimizing it, you're targeting multiple metrics, and so it's hard to know which ones to go after, how to make those trade-offs, which are constraints. Much more complicated landscape. And then on tools, yeah, especially with ASIC tools, you can't just give it some RTL and say, hey, go make me a chip. It doesn't work that way, right? That's not the way it works. You have to give it a full tool flow. You got to like hold its hand. You got to tell it nice things and give it positive encouragement. You think I'm joking, but no, you really need to give that tools some support. Constantly tweaking it. And basically people's entire careers are spent being the person that doesn't just run the entire tool flow, but even just a portion of the tool flow and understanding all the flags available to the CAD tools, how to configure them, and how they want to tweak them for the particular design. Entire people's careers, right? And the reason why this happens is because guess what? Compilers are used by millions of developers around the world. These big high-end CAD tools, especially the ASIC ones, are used by dozens of companies in the world. And so as a result, rather than making the tools that much more robust and easier to use, it's easier for them to have these high-paid support engineers. So yeah, if you're paying millions of dollars a year in CAD licenses, guess what? The CAD company will send you engineers to help you make sure the tools work for you in your case, right? But the result is that, yeah, they're not as automated as they should be. They aren't as robust as they should be. And guess what? There's a lot of CAD tools whose job it is to make sure the prior CAD tools didn't do anything wrong, right? So, you may hear things like LVS or DRC. I won't go into this in this course, but those technologies exist because guess what? The other CAD tools, not just sometimes, frequently make mistakes. That being said, I will give a shout out to the Open Road, Open Lane project to hopefully fix this. There's a huge open source effort, and perhaps by taking this out of industry's hands and putting it in the community's hands, we'll actually have robust, reliable tools. I would hope so. Cool. Okay, so at this point, perhaps I may be scaring you off with hardware design, but trust me, it's still fun. So what are we going to do? Well, remember from the very first lecture, I presented you two philosophies. Extremes, not the reality, right? Waterfalls, kind of classic way of building hardware where you're kind of very careful every step of the way. You say, I'm going to perfectly design this, perfectly specify it, implement it, etc. And I've been pitching all quarter. Close the loop, iterate, see the big picture, the Agile approach, right? And I want to keep repeating, right? It's because you're doing Agile doesn't mean you don't have a plan. It just means that the goal is to get something working as soon as you can and then start revising and extending. So you want to have kind of, the things mostly in place, the skeleton in place, a fuzzy copy, whatever you want to call it, something going, and then you want to go ahead and actually try and optimize it. And so, yeah, I keep saying close the loop and making this circle off the quarter because, yeah, it's the whole point, right? You design it, implement it, optimize it, verify it, and then you can do this multiple times. You can keep doing it. Okay, so for those unfamiliar with hardware design, what are the main stages of actual chip design? This is a highly oversimplified diagram, but basically, if you have RTL coming in and you hope to get your design back out the other end, in between the three major phases are synthesis, which is taking your Verilog, whatever you have, and turning that into actually the technology you're using, placing those components in hardware, and then actually routing the connections between them at a high level. This is overly simplified, right? A realistic flow will have many, many more boxes. And it's not just a single linear line. They often loop backwards. Okay, after I place and route, I'm going to go find a critical path. So then you go resynthesize that portion to be faster and then replace that to fix the critical path and then reroute it, etc. It's much more complicated, but these are the main steps, right? So synthesis is kind of turning their Verilog into actual technology. What logic gates are in your standard library for your standard cells in your ASIC, or perhaps what components like LUTs in your FPGAs are using. Where does it go physically, and how do you connect it all up? And so yeah, this is just to get the first design, but honestly, you have a lot more steps. There's a lot of concerns. For example, how do you make a chip such that when it's being manufactured, the factory can quickly check to make sure it was correctly manufactured, right? So designing for test, DFT, right? It also turns out, of course, when you're designing for high volume products and you have a very advanced feature node, even just manufacturing a chip requires changes to design to make it more possible to manufacture. That's referred to as DFM, or design for manufacturing. So there's a whole bunch of complexities there. We have a growing Cadillac courses here in Santa Cruz on this kind of stuff, such as 222A, 222B, et cetera. And beyond all these design changes in hardware, as I mentioned a second ago, these CAD tools and all this design work for us are not perfect. And so we got to keep constantly verifying every step of the way along the way to make sure we aren't getting a buggy design. Cool. Okay, so with that background for why we're doing design optimization, let's talk about memory. So why am I so excited about memory, so worried about memory? It's a big cost. For almost any hardware design, it's a really big cost. Just recently, talking to a faculty colleague, we were contemplating about future research, and we realized some of the design aspects, and we realized because of the nature we were building, we basically had no budget for memory. And guess what? When you're in that situation, it's a very exotic workload. There's only a handful of workloads out there that have so much compute and so little memory usage. Basically, every workload has some amount of memory. And as a result, memory is a large part of physical cost. And so when you talk about offshoot memory for a system, whether it be a small little device or a big server, it can add up, right? The offshoot memory is actual components itself. You have to buy those chips too. If you look at like a server, for example, there's a integer factor more amount of silicon area in the DRAM than there is in the CPU, right? So CPU maybe, let's say 500 millimeters squared. If you max out the DRAM capacity in that thing, you might have, I don't know, a couple thousand millimeters squared of DRAM silicon, right? So you're really going to burn up on DRAM. Yes. So yeah, to respond to the question of, well, wouldn't memory be an older process, so maybe it's less dense? Well, DRAM is all about cost, right? So they're going to try to make that as dense as they can. That being said, yes, older process, need to make room for the capacitors. I still suspect, even if you normalize for technology, if you count transistors, there's still more transistors in a server maxed out with DRAM than there is for compute. I would suspect there's still going to be more. And the point is, even if it's not just silicon area, right? You look at like, what's your motherboard, right? A large fraction of a motherboard or printed circuit board is going to be all that traces of wiring to get to the memory, right? That's physical cost, right? And then on the chip itself, you have, on your area of a chip, you have the compute, you're actually building stuff, but also all the pins to get to your offshoot memory, that takes area as well. And so once again, adding on the cost. The bigger your chip is, the more expensive it is to make. That's just offshoot memory. Now I'm talking about on-chip memory that makes your chip bigger and consumes a significant amount of area. For example, on a CPU chip, you might spend on the order of half of your area on SRAM for caches, right? So the size of your CPU chip directly corresponds to cost. And so if you can shrink your design and have it take less area, you can save money. In particular, if you can get away with less memory, you should, if you can. So that's the cost reasons. Performance reasons, memory is also often a limiter, right? As we all know in computer architecture, right, DRAM latency is insufficient for every instruction. We don't want to be executing out of DRAM. We have to have caches. But also bandwidth can be limiting, right? If you look at, for example, GPUs, what makes GPUs so awesome, in many cases, because they just have so much more memory bandwidth, right? Because HBM is all this, high bandwidth. And so actually, to really drive this point home, if you look at the newest Intel Sapphire Rapids, which came out, benchmarked only recently, for some workloads, there's like a 4x difference, the exact same CPU socket, on whether data is coming from DDR or from HBM. And that tells you the importance of bandwidth. So it's like really just it's the bandwidth limited workload. If you give more bandwidth, it can go faster. And if you don't have enough bandwidth, you're limited. So it's important. So yeah, so bandwidth is really important. Latent memory is really important. And so why do we even have memory in designs, of course? Well, obviously it holds the data, application data, intermediate state. If you want to think about it more philosophically, it's kind of fun to appreciate this for a moment. If your memory is like an all-purpose connector, or if you imagine what your computation is, perhaps with some sort of graph where I have this piece of data needs to operate this piece of data, the data flow graph. Memory is a way to communicate data in time, right? In other words, if you know the exact combination of who's producing data and who's consuming data, you can often turn it into a custom data path, right? You can say, oh yeah, well this component produces something, this component consumes something, wire it together, we're happy. But if you don't know who the producers and consumers are, often we put things in the memory as a way to kind of hold on to it for a while until we know who needs it. Or because often that relationship is not known in advance. So like I said, memory is a way to communicate data in time. Beyond the philosophical aspects, right? Just think about it more about you're going to need memory, and we want to worry about it for both cost and performance reasons. Okay, so for the brief architectural primer on memory, a few things to keep in mind, right? So reminding people of terminology when I say capacity, referring to how much data can hold. Latency is how long it takes to access the memory. Bandwidth is the data transfer rate, so in other words, data over time. A request is, something that we, send to memory. Oh, I want to do a read or a write request. The access width is how much data is transferred at a time. And then you may hear me say use the term port, right? So port refers to the ability to, access memory. And so it's no longer a philosophical concept, right? When we're writing software on a CPU, we say, oh yeah, I'm going to load and store to memory because there's kind of this one memory, which is DRAM. Here, this memory could be DRAM, it could be SRAM on chip, it could be BRAM and FPGA, it could be anything, but it needs to be concrete. It's just hardware, right? So we actually have, to actually talk to memory, we actually talk through a port. So perhaps you have a write port, you can have a read port, you actually can have a read/write port, meaning you can do one or the other per cycle. If you have memory capable of doing two different operations at the same time, that means that memory has multiple ports, right? So number of ports is an important constraint because very often we'll have a lot of consumers that want to access memory, and we can't put that many ports on memory. Especially if SRAM, there's a limit how many ports you can have. That's going to be a limiting factor. Additionally, when it comes to architecturally, you may hear the term requests in flight, which is basically saying how many memory operations we have going on at a time. So if you have a one-cycle latency, this is not too common, but if you have a multi-cycle latency in memory, because that latency, you don't want to have multiple things in flight to get some more throughput, that's when that term comes up. Question, yes? For SRAM. In practice, 2 on an ASIC is not unreasonable. Or not unreasonable, this is common even. 3 can be done. For a single SRAM array, going higher than 3, doable but rare. What do you mean by? Oh, that depends on. So yeah, the question is, okay, how big is a single SRAM array? That really depends on how you're working from memory compiler or your foundry for an ASIC. For an FPGA, right, you don't have okay, it's not seen as SRAM, you see it as BRAM, right? So BRAM's FPGAs, for example, a Xilinx style BRAM is going to be 32 or 36 kilobits, right? So on a BRAM, you often have 2 ports, right? And that's the thing. If you have like 4 ports of access needed, that's not going to have to BRAM because there's too many ports, right? But if you can get your access keys down to 2 ports, then yes, then you can use a BRAM. So so that's kind of corresponds to that same kind of constraint. So I said 2 ports is doable in common. More than 2 for a given, low-level memory is going to require some cleverness. So we'll talk about that later today, about how to handle that when your technology is once you have that many ports. So for those of you who are architecture from me, you know I love this law. I can't stop talking about it. I'm going to keep talking about it, right? Little's law, right? So it's the way you relate latency, parallelism, and throughput. So I mentioned this a moment ago. Imagine you have a high latency memory and you want to get more data out of it. Well, you can have more requests in flight, right? You're going to increase your throughput. And so this is a simple result from queuing theory, which actually holds, right? Like it seems so simple. Like how does it always work? If you treat these terms as averages, it does always work, which is pretty cool, right? So, whatever your average latency is times your average throughput is the average amount of stuff in flight. Now, perhaps depending on your units, the units of parallelism could be number of requests. It could even be bytes, right? Bytes are in flight, for example, depending on how you do your units in this. But this gives us a way to appreciate things. So, for example, as we go through our designs, perhaps in order to increase throughput, we're often going to increase parallelism if latency is fixed. But if we can reduce latency, for example, then if we reduce latency and we keep parallelism constant, then basically that means we can have even higher throughput, right? Because it's getting more done. So it's a fun way to kind of keep track of all these trade-offs. Cool. Okay, so as we spoke a second ago, what are the constraints on memory? So very often, latency is the thing that drives us architects' bets. So for off-chip, DRAM latency, oh my gosh, yeah, we're tired of waiting for DRAM latency. It's too high. Guess what? On-chip, SRAM latency, also a problem, right? Typically, the SRAM latency, unless you have the absolute best foundry-provided, memory compiler SRAMs, it's usually going to be worse than your clock cycle. In other words, a one-cycle SRAM access will not always be easy to do unless you really, really have a fancy SRAM. So yeah, latency is always a problem, right? As discussed, perhaps you want more ports to your memory than are physically easy to build, right? Maybe you want 4 ports to your memory. And guess what? You only get 2, right? So how do you handle that? Or based on enough bandwidth. With regards to ports, for example, years ago I saw some talks at a conference. There was a paper-worthy contribution to talk about how do you build a 12 read, 4 write memory, right? That was a paper. Because yeah, that's not easy to do. There's a lot of artificial tricks and circuit tricks you can do to make that happen. And they were discussing that. And you can imagine architecturally why you might have that. For example, for a register file on a big superscalar out of order processor, yeah, if you want to go 8 or 12 wide, let's say you want to go 8 wide and you expect each lane in your CPU requires 1.5 operands on average, and you're going to need 12 ports, right? So architecturally, you're going to have that need, but physically, it's not always possible. So we're talking today about how to kind of solve that. And that's the kind of thing. Architecturally, what can you do? Given your physical constraints, how can you change your design to handle that? Well, first off, do whatever you can to reduce how much capacity you need and to use the cheapest memory possible, right? We also want to reduce the amount of bandwidth we need, and architecturally, we can also change our design to handle higher latencies, right? How can you tolerate that? And so, in terms of technologies, my handwave for today, you've already heard them mentioned in passings, right? Registers, or used most often in this course. When we talk about SRAM, DRAM, of course, exists, even though we don't use it directly in this course. And then other things like phase change memory and flash also exist. Cool. Other concerns or questions? Oops. Yes. I mean, you make a flash controller in Chisel, maybe. Correct. And actually, yeah, so one of the early RISC-V adopters was Western Digital using it for drive controllers. They did not necessarily use Chisel. They used System Verilog. But, yeah, definitely RTL gets involved in this mix for sure. Cool. Okay, let's talk about some ways we can intervene. So, as I mentioned a second ago, you want more bandwidth or more ports than technology to what you have, right? I told you, oh yeah, you have SRAM that only lets you have 2 ports to it, right? So how do you get 4 ports? Well, secret is called banking, right? In other words, you can take multiple memories, put them together, and by doing that, you can give the effect, the illusion of having more ports, right? So, to kind of show this conceptually, let's say I want to have a certain bandwidth going to memory. Well, I can't build up technologies I have. So instead I can build maybe 2 smaller half-size memories, and the 2 of them working together can give, twice the bandwidth that would have been possible technology otherwise, right? Now, this is a very general, broad architectural concept. You can imagine, all sorts of caveats and nuances to when you apply it. But that's the general idea, right? You have, rather than one big monolithic memory, you have multiple smaller memories working together, and they can service requests independently, and that way you can get more parallelism, right? So in terms of throughput, right, the latency of the memory is perhaps unchanged. Maybe it's a smidge faster, it's some like logarithmic improvement. But the key thing is that by having, 2 banks, in this case, increasing parallelism, we can increase throughput by Little's law, right? That's what we're doing, right? And yeah, but guess what? In Chisel, you can imagine having some knobs to easily change how many banks are inside your component, and you can have that as a knob you can turn to adjust to whatever implementation knowledge you're using that day. And to be honest, actually, to have a standardized library for doing banking or memory design is always kind of one of my pet projects in pitching for the project. If someone's curious for a project, yes, some of the things I talk about today, maybe worth considering how to automate that into a package. Yeah. Yeah, absolutely. So the question is, if I originally had 1 port, now I have to expose 2 ports to the outside world. What about the, relative nature of those 2 addresses going to 2 different ports? Yeah, that absolutely comes to your point, right? So that's absolutely a concern, right? And so, as you mentioned, if you have multiple banks, how do you choose where data goes and how do you route requests, right? So you can think of it as, for now, 2 different high-level trade-offs, but there's 2 different high-level approaches, but there's many more approaches and combinations possible. So the simplest one would be just partitioning it, saying, you know what? If I have 2 banks, each bank is half of the memory, and based on the address, you can tell which one it's going to. And so that way, a request is only bound for exactly 1 bank. Alternatively, so that's going to help you in cases where you want to get more bandwidth, and you're kind of trusting the user has enough variance in their addresses, this works out. And you can imagine, actually, architecturally, you can almost guarantee this works out really well sometimes. Let's say architecturally you're building like SRAM for like instruction fetch. If you have a 2 wide processor, you're going to grab PC and PC plus 4 every cycle. So guess what? If you have 2 banks that are interleaved every 4 bytes, that way you can use both banks every cycle, right? For example, so you can kind of compound on it. Or maybe you want to interleave it. You actually want to use 1 bank one cycle, 1 bank next cycle, in which case you have each bank be 8 bytes wide or something. there's trade-offs, right? The other alternative is to replicate data across banks, meaning all banks hold the same data, which at first may sound kind of, redundant or wasteful. Like, why would I do that? You're doing that to increase the number of ports, right? If I only have technologies that have 2 read ports in my SRAM, how am I going to get 4 ports? Well, if I have 2 copies, each has 2 ports. We'll get between 2 of them, now I have 4 ports, right? That's kind of the point. So yeah, so replication is another way to kind of take advantage of. So you can see there's some nuance here about how are using these banks to work together. But the key idea is, yes, I have these banks and somehow I'm giving the effect of having more bandwidth, more parallelism, more ports, etc. To the point that you brought me to change the slide, the original question. What about, how independent are these ports? Are they independent ports? Are they shared ports? Has nowhere to go? There's some trade-offs there, right? And it's one of these things where design for this memory isn't completely in isolation. It's often done in conjunction with surrounding context and know how to interface with it. If you have long latency requests, perhaps all these banks can go through the same port. If you really have low latency requests and just tons of requests, then perhaps each bank needs to have its own port, right? For example. And then what's interesting about this, I've been talking about this so far in terms of bandwidth, but banking also comes up for capacity, where sometimes you literally just want more capacity. You build any given memory only so big, and so in order to have more memory, you have more memories, and thus you end up with more banks just because of capacity reasons. So some situations, often like even in a server, for example, if you really want to max the capacity in a server, the bandwidth effective per chip in your one of your DRAM DIMMs is actually quite low. And the reason why is you turn all of your knobs towards capacity, right? So you actually have surplus bandwidth in some ways, which is rare. It seems kind of odd, but you do. Cool. Yes. How do I make sure things are atomic if you do read it right? Well, that's something that you can have some control over as the person doing the architecture, right? You can decide, okay, well, how am I going to do this? If I have multiple ports, if there's going to be any kind of atomicity promised to the user of your component, it's up to you to implement, right? Now, guess what? When it comes to memory, within Chisel, for example, there are things like if you have 2 ports in your memory, let's say one's a read port, one's a write port, and they're both going to the same address, does the read get the old data value or the new data value? That actually depends what technology you're using, right? Some FPGAs, the MASICs are different, right? So Chisel actually has a way with the, using more verbose arguments in the memory construct, you can tell it which one to use, which behavior to have. So there's actually some ways to literally tell that in Chisel, but also when it comes architecturally, it's up to you to kind of make that enforced. Cool. Okay, now we can keep going then. So, solution 1 was banking. Solution 2, I'm going to kind of pitch as a broad strokes, and I'll show you some concrete examples of this. So, the idea is to recognize that sometimes the demand for some resource, in this case memory, bandwidth, is not uniform, right? You have a lot of demand, and then it's low. And so, we've all been on a road and seen traffic and been very frustrated. Oh my gosh, there's traffic. Why is this road bigger to handle the traffic? Well, making the road bigger costs money, right? And it turns out for even the most busy freeways, if you look at that freeway, not just when you're driving on it, perhaps during rush hour, but 24 hours a day, 365 days a year, and average how many cars, per hour drive across it, the average, throughput, cars per hour across a piece of road may not be very high, right? And so that's kind of the point. There's actually a substantial gap between the average throughput versus the peak. And guess what? When the peak is limited by the capacity, we all notice it. We all feel it. Oh man, there's a line, there's traffic. But as engineers, we can appreciate that, if there's a big gap there, that's very wasteful, right? We're paying for peak when if we could pay for average, we could pay a lot less. It'd be a lot cheaper, right? So that's the goal when it comes to architecturally is to recognize if our design has very bursty traffic. How can we somehow turn that bursty traffic into a uniform, more smooth traffic, right? That's the goal. And, in the real world, we often do things like encouraging folks not to drive during rush hour or stuff like that to try and smooth out traffic, work from home, that kind of stuff. Same architecturally. Architecturally, we think about how can we make this bursty traffic for DRAM more smooth. And that said, like a lot of optimizations talking about today in terms of memory are all things that you should be considering if you have a project that involve memory, which most of you will, because guess what? Memory is in almost everything. Okay, so one optimization is to overlap computation and communication, right? So if you kind of think of your workflows, oh yeah, I need to get the data, work on it, get the data, and work on it, well, guess what? If you're only doing one of these things at a time, that means you're not doing the other one, right? And so as a result, your communication's on, off, on, off, on, off. So this idleness we want to fill up, right? So if you're able to overlap communication in the background of the computation, then yeah, it can be more efficient. So if you want to put on your architectural hat and try and label what's going on here conceptually, you could remind yourself, oh yeah, this is a form of pipelining, right? That we have more things in flight at the same time, right? This is kind of a form of parallelism technically. But if you can do this, it's cool. And guess what? When you're actually designing hardware, you can do this, right? Sometimes as humans, we think, oh, I only do one thing at a time. It's hard for me to multitask. It's not easy. Guess what? In hardware, you can just build more hardware to do the multitasking, right? So this is very doable. So when you can artificially change your design to fix this, you should. Okay. Another intervention for the same notion is double buffering. So you might say, okay, how do I do computation and communication overlap? How to actually implement those two things? Well, one way of doing that is to have two memories, right? Because you can imagine that, while you're computing on one memory, you could then be transferring another memory. So basically, computing on memory one, transferring memory two, and then the next phase, you do the reverse, right? So that way, why would you do this? Well, as I mentioned earlier, oftentimes memories have a limited number of ports. And so, for example, if you have a port on memory you're using to access the data, to actually do computation, there may not be additional ports for you to do the communication as well, right? But if you have two memories and you double buffering, that way you only need ports for computation or communication at one time, and you can kind of squeeze things in there. This is a common tactic. People often even do this even just one large memory and just two different address ranges is in there. But basically, in other words, setting up your future task while you're working on a current task, right? That's kind of the key idea. Cool. Questions? Okay. So coming back to Chisel, right? What are we going to do to actually instantiate memories, right? So if you're doing an offset memory, that's not a small decision, right? That's a big decision in terms of, what technology you're using, what interface you're using. There's huge implications, right? Let's say you're building like an ASIC. Whether you're using DDR, LPDDR, or HBM, or even HGDDR, all four of those families of technologies, that's a big change, right? That's not something you just kind of flip the switch on. Now, for some of those interfaces, you have some choices about how wide is the interface, what clock rate, which generation, sure. But for the most part, offshore memories is not a, spur of the moment agile decision, right? This is more of a deliberate, planned out thing. And you're going to be very careful about it because guess what? It costs a lot of money. So you're going to figure out, how much bandwidth do I really need? How much capacity do I really need? What is the cheapest memory I can use? And you're going to try and make that work. The rest of the design is to kind of fit in that constraint. So let's say, for example, you settle on a particular, DDR technology and a particular DDR generation. It's up to you to make sure the rest of your design can be satisfied by the latency and bandwidth opportunities provided by that memory, right? That's now a constraint in the rest of your design. Okay, so now that we're, if the off-chip's not the purview of us agile designers, for on-chip, you still have some choices, right? So in an ASIC, right, you often have a choice of, for a given memory, you can do it with registers or SRAM. Technically, there's also latches, but we'll ignore those. And so depending on how you're building things, SRAMs often come from your foundry in preset sizes. And foundries, for our SRAMs in our foundry, these are guaranteed, good SRAMs. But those sizes may not exactly correspond to your use case. So it's kind of up to you to figure out, okay, well, given those preset sizes, how does correspond to what I need? Or, of course, you may shell out for the money for a memory compiler that actually, attempts to generate the right memory arrays for you. And so, yeah, when you are working with these, ASIC SRAMs, you have to literally say, I want, this particular instance, this particular SRAM map to be instantiated, right? Sometimes you want to treat which one you're using to kind of see how it changes power, performance, area, that kind of stuff. But it's a pretty deliberate, intentional thing that's, done consciously. Interestingly, in FPGAs, you have a lot more choices, which is kind of surprising. You think it would be reversed, right? But in FPGAs, you have registers. You can turn LUTs into LUT RAM, right? You have BRAM or block RAM, and even sometimes URAM or ultra RAM, right? So what's interesting is the FPGA tools, compared to the ASIC tools, actually, I would say is a little bit safer, right? Part of the reason why, a little bit more robust. Part of the reason why is they have less complexity to deal with, but they also have more end users. And because they have more end users, they can't always have support engineers there. There's more pressure in the calculator to make the tools actually work. So take a FPGA tool such as Vivado, hit some buttons. It's gonna be closer to giving you a guaranteed design the first time than the ASIC tools were by a large margin, right? So when it comes to memories, the methodologies typically actually let the tools infer to memories. Now, it's not foolproof, right? It's not guaranteed. But ideally, you write Verilog in a way where the tools can infer what memories are possible, and they'll make better choices about, you know what, given the kernelization of this design, you should use BRAM, you should use LUTRAM or registers. It'll make those choices for you. And in my research group, we use FPGAs quite often with designs that originally started in Chisel, and we care about performance, so we'll look down at how they were mapped. We often find that our memories, this exact same component, just instantiated multiple times, it may be, we've seen it instantiated as both LUTRAM, BRAM, and registers in the same design, right? So tools will make those choices ad hoc as it makes sense. And so give it the opportunity to do so. For example, if you're targeting BRAM, you can't have a MEM that has like 5 ports, right? BRAMs and FPGAs are limited to 2, right? So you make sure architecturally that memory only has 2 ports. And if you do that, then there's a chance the Verilog inference by, a CAD tool or an FPGA tool will actually infer the BRAMs for you. Despite that, it's not perfect. That's why sometimes you gotta give the tools a nudge or use intrinsics. Question, yeah. Um, just in general, like I said, you spend all this time like on the ASIC. The question was, what do I mean by portable? You spend all this time on ASIC, and you're like, okay, well, this is the exact design size, the exact capacity for memory, the exact technology. Sure, you can pick the exact rate of arrays, and you're done. But like, your buddy comes to you next day and says, you know what, I want to now change the design size. And it's like, oh my gosh, I got to refigure out all the right SRAM arrays and that kind of stuff. So the point is to be agile, right? We want to be able to say, you know what, I can make these knobs, let the tools do the work. Now they're kind of fun. Yeah, so having the tools infer memories makes it easier to kind of change things rather than have to be dialed in. Because you imagine using one FPGA tool from one vendor, you have one set of things. Let's say you want to change FPGA vendors, which if you don't use intrinsics, actually isn't that crazy. Or maybe you want to go from open source to closed source or vice versa. If inference works, that's a better way of doing it. It's one of those things where try the inference, if it doesn't work, figure out if you can change your code so that inference will work. If that still doesn't work, then use the intrinsics. But try to avoid using intrinsics on the first step. It's kind of like, writing your own data structures in software, where the standard library data structures works, use those, right? If they don't work, think if you can change your code to use those. If that still doesn't work, then write your own data structures, right? So try to make things more automated when possible. And then finally, what does Chisel give you? So Chisel kind of is describing the functional cycle level behavior. It's not actually a physical design tool, right? So in other words, you say mem, and mem, by default says that is a 0 cycles to read, 1 cycle to write storage device, right? You can override the latency parameters, or you can use sync read mem to get, 1 cycle read, 1 cycle write, etc. And so on FPGAs, it actually works great. For registers at BRAM, URAM, that all works fine. If you want to do SRAMs on a real ASIC, you should use sync read mem to get the right functional behavior when you're developing and testing. But perhaps in the final version you push through the ASIC CAD tools, you probably will use a black box, which is a way in Chisel to wrap up Verilog, to wrap up the Verilog, wrappers, which in turn wrap whatever, hard-coded mats you have for your SRAM technology. One detail I want to point out, so in Chisel, we mentioned there's 2 ways to declare ports. You can have ports that are implicit, where you declare memory, and later on you either read or write it. Or you can actually say, that memory dot read, that memory dot write, or you can even have a read/write port. And so sometimes, if you're not careful the way you express your Chisel, you can have your design such that, in one place you're reading it, another place you're writing, and as an architect that you're never going to simultaneously read or write. That may not be obvious to the tools. So if you know you really want just one read/write port, for example, you might need to restructure your code. It won't be as pretty, I'm sorry, but you can use some wires to do this, such as clear really just one port. Cool. Okay. So appreciate all the questions today. So what have we talked about? Well, number one, I'm just trying to expose folks who maybe coming from pure software background, what's involved in hardware design optimization. And whenever you're optimizing anything, right, make sure you know what your targets are and what's the reasonable goals, right? So in the case of us designing hardware, our competing point is a off-the-shelf microcontroller or small CPU or SoC or whatever, right? That's what we're competing against, right? Or even a big CPU, right? Perhaps a server CPU. But the point is, Why should someone build specialized hardware when they can go get a CPU? It's much easier to write code for a CPU to go design and build a hardware, right? So that's your baseline you got to beat. You also make sure you know what metrics you're going for and how do you do better on those. As always, see the big picture, close the loop, find one advantages of closing the loop early. And by that I mean not just getting something functionally working in chisel early, but actually passing that chisel through the tools, getting Verilog, and then passing that Verilog to your backend tools early. You can see issues early on, right? The last thing you want to do is spend a year writing chisel and have this chisel design you convince is perfect, no bugs, perfectly verified. And you pass it on to your hardware design team, and they take the Verilog and like, this won't work, right? And now what, right? No surprises, right? Get the chisel working as early as you can, get the chisel to Verilog to the CAD tools as early as you can. So that way you start seeing the big picture, right? You can be aware of, okay, how's this going? You also can be aware of how your costs are lining up, right? Where sometimes it's not obvious at the beginning, what's going to eat your area, what's going to eat your performance, what's going to eat your critical path. Getting involved with the physical tools earlier helps you do that. In this course, unfortunately, we do not do anything with the physical tools. But beyond this course, understand it should be really important what you're doing. And then when it comes to memory, we talked about a few ways to improve things. Memory is said because it's like half the area on chip and a lot of the pins for off chip. It's the biggest thing, right? For optimization, go after the big thing first. Memory is often the biggest thing, so let's go after that first, right? And so, number one, pick the right memory technique. That's an artificial choice, about which capacity, style, technology, etc. And optimizations, oh man, we covered so many today, right? We talked about banking, traffic shaping, communication, computation overlap, and double buffering. Cool. Any other questions? So as I mentioned earlier, I'm, kind of lobbing this project idea out there of, gee, wouldn't it be cool if someone had a, chisel generator where you could say, hey, I want a memory. And from a user point of view, that's pretty simple, right? But then under the hood, it knows what your implementation technology is and perhaps does the banking or appropriate double buffering under the hood for you such that, if you ask for 9 ports, it goes, oh, wait, you asked for 9 ports. I'm going to do 2 ports at a time. I'm going to replicate and bank for you internally. That could become a fun project. Cool. Okay, with that, that's all, folks. Good luck on the project.